Okay, this is my solution for the problem that we did Monday of week 2. And we were looking at a line of charge. So you can imagine maybe a rod. And we were looking at the electric field along the line that bisects the rod. And once again, it had some extent h on one side and on the other side h. Okay, we're out here some distance x. And so we were told that the line charge has a linear charge density of lambda, so the units of lambda would be coulombs per meter. And we started by thinking about just this little chunk. This is a little chunk dy. So the y-axis goes up like that. Next. And we said that due to that little chunk, at the point we're considering, I'll carefully draw a line here, to the point we're considering, due to a positive charge, there's a repelling force this way. And so we can write down just that little bit of the electric field. And so due to just that little bit of charge, there's a charge, which means a charge density times the length, dy. And this little piece of dy is located at some location, y. And so the distance between that little piece of charge and the point I'm considering is x squared plus y squared. And I square it, and I put a k out front. And now what I have is the field due to that little differential piece of charge. In fact, we could call this dE. Now, it might be tempting to then just integrate this and add all the electric fields, but what I have to realize is that by the time I get down to the bottom, for example, now there's a field going to be going up this way. And so, in fact, once again, I'm going to use the symmetry of the problem with the idea that only the horizontal part survives. Only the horizontal. Survives when we add. The vertical parts cancel. Or I should say add to 0. So I only want the horizontal component, so just as I've been doing, if I call this theta, then this is also theta, and the horizontal component this time is going to be, you might call it a cosine theta, but it's going to be horizontal component, so cosine x all over the square root of x squared plus y squared. This is basically cosine theta. Cosine theta. So I'm going to multiply that by my little piece of electric field. And now I'll integrate. So I'll simplify this. And I'm going to go from minus h to h again. Notice that I'm integrating over dy. So this integral, minus h to h, k lambda x, and then I have dy and x squared plus y squared, 3/2. This stuff can go out front. It doesn't depend on y. Remember, x is a constant in this problem. So I look at this integral and I start to realize that I'm not exactly sure how to do it, so I'm going to pause and go consult Wolfram alpha. Okay, I'm back. So I consulted Wolfram alpha, and I learned that this integral right here is equal to y all over x squared plus y squared. And so the whole thing then is evaluated from minus h to h. Okay, So I'll sort of chug through here. Page 2. K lambda x. And then we go from h all over x squared, square root of x squared plus h squared, minus h all over x squared plus h squared, still positive, which is equal to just two of them. So 2k lambda x h, like I'm spelling a strange word here, divided by x squared, square root x squared plus h squared. One of the sets of x cancel. I divide both sides by x, and I'm left with 2k lambda h x square root of x squared plus h squared. Okay, that's the answer. Now, a couple things you might want to notice. Let's say, for example, and as was done in the book, you were given instead the total charge, Q. That's the same thing as lambda times the whole length of the rod, which is 2h. So I could also write the electric field as K. Let's see, lambda to, Q. There we go. All over x square root of x squared plus h squared. You should also notice, this is more important, also notice what happens if we take an infinite line charge. And I'm going to use a little bit of a trick here. I'm going to pull out a square root of h squared, or h, from both sides, from both the top and the bottom. And so I get E is, let's see, K, 2 lambda h all over, and now what I'm going to do is I'm going to write x and then an h, which means this square root then has to become x over h squared plus 1. So why did I do that? I did that because now that if I let h go to be very large, this piece is going to go to 0 because these h's actually cancel. And so what I'm left with is something pretty simple. E is just k, 2 lambda all over, the only thing left is x. And that is the answer. Ta-da!